One machine controls the future of every phone, every car, every fighter jet, and every AI system on Earth. It costs more than $200 million. It is built by a single company in a single country, and for 20 years, nobody else on the planet could copy it. That company is ASML, and until recently, China could not buy one, could not build one, could not even see inside one. Then, in a factory floor the size of an airport hangar, Chinese engineers switched on something new. By the end of this video, you will understand why this machine, however unfinished, however imperfect, makes China the most dangerous player in the global chip war. Not because it is better than the original, because it doesn't need to be. If you run a company, invest in one, or simply want to understand where the next decade of global power is heading, this is the story you need to know. Because what's happening inside this factory is not really about chips. It's about who controls the 21st century. To understand why this machine matters, you have to understand what it actually does. Every advanced microchip on Earth, the one in your phone, your car, your bank's servers, starts as a blank silicon wafer. To turn that wafer into a chip, you need to print billions of microscopic circuits onto it. Circuits so small you could fit thousands of them across the width of a human hair. To print something that small, you need light, very specific light, light with a wavelength of just 13.5 nanometers. This is called extreme ultraviolet light, or EUV. For almost 2 decades, only one company on Earth could generate this light reliably enough to build machines around it. That company is ASML, based in the Netherlands. Every single advanced chip made by TSMC, Samsung, or Intel passes through an ASML machine at some point, no exceptions. This gave one small Dutch company more leverage over the global economy than most nations. And in 2019, the US government used that leverage. Washington pressured the Netherlands to block ASML from selling its most advanced EUV machines to China. The message was simple. If China cannot access this light, China cannot build the chips of the future. For years, that strategy worked. China's chip industry stalled at older technology, while the rest of the world raced ahead. But something happened that very few people expected. China didn't try to buy the machine. China decided to build its own. And this is where the story gets interesting, because rebuilding an EUV machine isn't like reverse engineering an iPhone. It requires solving 4 separate, almost impossible problems at the same time. Problem 1. How do you generate 13.5 nanometer light in the first place? You cannot simply build a laser tuned to that wavelength. You have to manufacture the light through a violent, controlled explosion 50,000 times every second. Here is how ASML does it. A microscopic droplet of molten tin, smaller than a grain of sand, is fired into a vacuum chamber. A small laser flattens it into a disc. Then, a far more powerful laser strikes that same disc a split second later, vaporizing it into plasma at 200,000 degrees Celsius. As that plasma cools, it releases a burst of EUV light. Now imagine doing that 50,000 times every single second, hitting a target smaller than a period on this screen without a single miss. It took ASML decades to make this reliable enough for a factory floor. This became the industry standard, and when Chinese engineers sat down to solve the same problem, they faced a choice most people never think about in business: copy the winning formula, or bet on the approach everyone else abandoned. They chose to bet on both. Here's the twist nobody saw coming. 20 years ago, ASML actually tried a different method of generating this light. It's called laser-induced discharge plasma. Instead of firing 50,000 flying tin droplets a second, this method uses 2 rotating metal discs coated in liquid tin sitting between a bank of fully charged capacitors. A small laser triggers a cloud of tin vapor between the discs. Then the capacitors release a massive jolt of electricity straight through that cloud, crushing it into plasma using nothing but a magnetic field. No giant laser required, no flying targets to chase. On paper, it's simpler, cheaper, and more efficient. So why didn't ASML use it? Because 20 years ago, this method hit a wall. As engineers pushed more energy into the plasma, it grew bigger, but not brighter. And a bigger, dimmer light source is useless in a factory that needs hundreds of watts of stable power, hour after hour, day after day. This approach topped out at just 30 watts of usable light. Now, here's where China's bet becomes fascinating. China isn't claiming this old idea was secretly better all along. China is betting on something far more strategic, that 2026 is not 2006. That materials, electronics, and manufacturing have advanced enough to finally unlock an approach the rest of the industry left behind. Reports suggest China is now pursuing both paths simultaneously, the proven method and the abandoned one. And that alone tells you something important about how China approaches technological warfare. When you're locked out of the winning strategy, you don't just copy it slower. You look for the door nobody else is guarding anymore. But even if China solves the light, that solves less than half the problem. Because now you have to aim that light. And at this wavelength, the laws of physics stop cooperating. Every lens you've ever used, in your glasses, your camera, your microscope, works by bending light. But at 13.5 nanometers, almost every material doesn't bend this light. It absorbs it. So the entire optical system had to be reinvented. Instead of lenses, engineers use a chain of mirrors, precisely angled to bounce the light step by step toward the silicon wafer. But these aren't ordinary mirrors. Each one is built from dozens of layers, each only a few atoms thick, alternating between molybdenum and silicon. And every time the light bounces off one of these mirrors, it loses roughly 30% of its strength. China split the problem into pieces and assigned it to specialized state research institutes. One of the most important, the Changchun Institute of Optics, had already built world-class mirrors for space telescopes. But an EUV mirror is a different universe of precision. The surface has to be smooth to within 50 picometers. That is smaller than the width of a single atom. And it's not just about building the mirror once. Inside a working EUV machine, that mirror sits inside a storm of superheated tin plasma and intense radiation for years without degrading. Reports suggest Chinese institutes have already built and installed domestic mirrors into a working prototype system. But matching Zeiss's reflectivity and long-term durability is an entirely different challenge, one measured in years of production, not a single successful test. So China made a trade-off that tells you everything about how emerging challengers compete against entrenched leaders. If your components are less efficient, you don't need to make them perfect. You make them bigger. Bigger collectors, longer optical paths, more mirrors. It's the engineering equivalent of a company that can't out-innovate a competitor, so instead, it outscales them. That is very likely why this prototype reportedly occupies an entire factory floor, while an ASML machine is roughly the size of a school bus. It's not necessarily a design failure. It may be a very deliberate compromise. Solve for scale while you're still solving for precision. And just when it looks like the hardest problems are the light and the mirrors, there's a third bottleneck almost nobody outside this industry has ever heard of. It's helium, the same gas in a birthday balloon. Helium plays a role nothing else can replace inside an EUV machine. It pulls heat away from the hottest components. It doesn't react with the delicate optics or the silicon wafer, and its atoms are so small, it's the only practical way to detect leaks too tiny for any other gas to find. A single advanced chip factory can consume between 5,000 and 20,000 cubic meters of helium every single month. And unlike oil, you cannot simply stockpile it for a rainy day. Helium is shipped as a cryogenic liquid. If it sits too long in transit, it slowly boils away and escapes into the atmosphere, gone forever. Here's the crisis. China imports roughly 85% of the helium it uses. Domestic production sits under 900 tons a year. Demand exceeds 4,900 tons. And historically, most of that supply came from just two places, Qatar and Russia. Now, think about the position China is in. It is trying to build a fully domestic, sanctions-proof chip machine while depending completely on a resource it does not control, sourced from countries caught in their own geopolitical storms. This is not just China's problem. It's the entire industry's problem. TSMC, Samsung, Intel, SK Hynix, every advanced chipmaker on Earth draws from the same fragile helium supply chain. Think about what that really means for a moment. China can spend billions of dollars. It can recruit the world's best engineers. It can build mirrors smoother than an atom. And it can still be stopped not by a rival superpower, but by a party balloon gas most people never think about. This is the uncomfortable truth at the center of every advanced supply chain. You are only as strong as your most overlooked dependency. Step back, and this story stops being about lithography altogether. It becomes a case study in how dominant leaders lose their monopoly. For 20 years, ASML's advantage looked unbreakable, protected by physics, patents, and 30 years of accumulated expertise nobody else could buy. But an advantage built on exclusive access, rather than genuinely superior economics, has a hidden weakness. It only survives as long as the access stays exclusive. The moment a competitor is willing to accept a worse, bigger, less efficient version of your product simply to remove their dependence on you, your monopoly stops being a monopoly. It becomes a countdown. This is the lesson every industry leader should sit with. Being the best is not the same as being irreplaceable. And the companies and the countries that assume their technological lead is permanent are usually the ones standing still when somebody else decides good enough is good enough. So here we are, a factory floor the size of an airport hangar, a machine less powerful, less refined, and less elegant than the one it's trying to replace. And yet, potentially, more dangerous than anything ASML has ever built. Not because it's better, because it doesn't have to answer to anyone. The real race was never about who builds the most advanced lithography machine on Earth. It's about who controls the machine that builds everything else. The phones, the cars, the weapons, and the artificial intelligence that will define the next 50 years. ASML spent 30 years building a wall nobody else could climb. China just showed the world you don't always need to climb the wall. Sometimes you just build your own mountain right next to it. If you had watched the entire video, you have surely liked the video. You should not miss the next video. Please subscribe and hit the like button.